Okay guys, in our previous video we looked at the definition of an arithmetic sequence, and that is to say that these are these sequences that from term to term either increase or decrease by a constant amount. That constant amount we refer to as the common difference, or D. So in this video what we're going to look at is kind of, considering that these sequences are so well behaved, could we come up with a way to write the rule for these sequences? And I would actually make the argument that on all of these sequences that we kind of tried to determine what the next term would be, we could tell you just because we knew what was happening to the term before. So I would like to make the argument that if we want to write the rule for the nth term of an arithmetic sequence, so arithmetic sequence, I think that, according to me at least, we would only really need to know two things in the sequence. And that is to say that if I knew the value of the first term, which is our A1, and I knew what it was changing by every time, I could tell you the value of the next term simply by taking our first term and adding on D. And as a matter of fact, for every consecutive term after this, so I've got my first term, my second term, my third term, we could say that I'm just going to continuously add on multiples of D. So you could see that to get to my second term, I would start at my first term and add on D once. To get to my third term, I would start at my first term and add on D twice. You can always see that to get to any individual spot, you would start at the first term and really add on D, not as many times as the spot you're in, but kind of one less than the spot you're in. So we're going to look at a rule for the nth term of an arithmetic sequence, and that rule is this rule that you see here. Now, again, because of formatting in PowerPoint, we're going to rewrite this rule on our own, and that's why I built in this little space up here. But the rule for the nth term of an arithmetic sequence is always thus. We say that the nth term always has a value of start at the first term and then just go up by D every single time that you go over by a spot. Now, one thing to keep in mind is, say for the fourth term here, we need to start at the first term and go up by D only 3 times. The fact is that I'm going to add D onto A, but always one less than the spot that I'm in, just to make sure that I don't add it up as many times as the spot that I'm in, but kind of one less. So this rule right here basically is going to give us the value of A sub n, or the nth term. So what are some things that are worth mentioning here? Well, the only two things that we need in terms of our grocery list in order to write a rule are going to be these two things right here, which A1 is our first term value, okay? And then we say D, which is our common difference, which, by the way, if you would like a symbolic representation of this, remember that D is equal to any given term minus the term value right before it. If you were to evaluate this, you would have your common difference. I only mention that because not all the time do we have the common difference just given to us. We have to do a little bit of side work to figure out what it is. So this is kind of a neat thing. Because they're so well behaved, we can write a rule very easily just using the first term value and the common difference. Then it becomes just sort of a plug and chug. So in terms of what you'll see here, it says A with this down arrow n. Just to give you a heads up here, this is A sub n. A sub n represents the value of the nth term in the sequence, so I can tell you this value if you know the value of the first term in the sequence, A1, and the common difference, D. N is going to represent the value of the term's position. So n, remember, is a position. Okay. So in terms of writing rules, let's take a look at how we could actually put this to work here. And so I've got a few situations down here, each a little different from the next, but in each instance we want to write a rule that would give us the value of any given term in the nth spot. So the instructions here say write the rule for the nth term of the following arithmetic sequences. So this first sequence here, what I want you to notice is that it's given to you in what we refer to as our roster notation. That is, it's already kind of written out. It's not given in a table. It's written side by side. So some things here. First one we're going to want to do is kind of see what our common difference is here. And so I noticed that from term to term here, just by observation, it's going up by 2 every time. But we could certainly verify this. If I took D and I said D is 3 minus 1, for these 2 consecutive terms here, I get 2. So I'm going to box this here. Somewhere you need to write down your D value. Now, remember what I said, we need our first term value as well if we're going to write the rule here. So A1 is going to have a value of -5. I'm going to put a box around this as well. So you can see here that if you know the first term value and you know that it's going up by 2 every time, writing a rule becomes actually fundamentally easier in terms of level of difficulty here. So our nth term is always first term plus going up by d every time times n minus 1 here. If we're going to write the rule then for letter A, which I'll kind of indicate here, we'd say our rule for the nth term is our nth term value has a value of a1, which in this case, a1, you can see it over here, is this -5. a1 has a value of -5. And it's going up by d every time, and our d value here is 2. So we can see that we have to put in our d value here. I'm going to put it in red. And then we take this times n minus 1. I'm going to go ahead and put kind of like a box around this, or circle it. Because here's the thing. This rule works just as fine this form as it does when we simplify it in just a moment. So what does this rule tell me? Well, it kind of says you started at -5 and you're kind of going up by 2 for every one of these n's, but we're not going to multiply it exactly by the position we're in, but kind of one less than that position we're in, since we didn't add it on to the first term to begin with. So this is our rule. What are we going to want to do from here once we get our rule written? We're always going to want to simplify after writing the initial rule. Okay, the initial rule, which the initial rule is this rule you see right here. So in terms of simplification, this is always going to involve two things. Simplify is going to mean that first of all we're going to distribute wherever possible, which is always going to be a coefficient of this n minus 1. And then what we're going to do is combine like terms. So let's go ahead and try that here. If we distribute this 2 here, what we're going to end up with is then our nth term has a value of -5 plus 2n minus 2. And with respect to combining like terms, we can tie these two together here. Let me kind of go down a little bit. Ooh, running out of space. Suppose we'll pick it up and carry it over here. Our rule for the nth term then is going to be a sub n is equal to -5 and -2 is a -7. We get 2n minus 7. So here's the cool thing about this. Without doing a whole lot of work, we just needed to know the first term value and what it's changing by every time. We can really easily write the equations of these things. And as a good practice, it's always good to test your rule. What if I wanted to know the value of, say, the 1, 2, 3, 4, fifth term is 3? You know, if I say a5, does this rule work here? Well, I get 2 times 5 minus 7, which, by the way, is 10 minus 7, which last time I checked is indeed 3, like we need to have a value of here. So pretty cool. If you are given the terms in roster notation, we just want to identify what's your first term and what's it changing by every time. Now, letter B here, let's take a look at this one. This should say a sub 1 equals 10 and d equals -1.5. Remember or recall what we mentioned previously. In order to write this rule, we need to know two things. A sub 1, our first term value, and what it's changing by every time. And in this case, they're just kind of literally given to us. And that might be true for certain cases that we actually just know these things. So in this case, our nth term value would be a1, which is our 10, plus -1.5 is our common difference here, so going down by 1.5 every time times n minus 1. And we're just going to simply simplify this here. So we get 10 plus a -1.5n plus a positive 1.5. This time when we stick 10 with 1.5, what we get is this. We get -1.5n plus 11.5. So I'm going to box this, and again, it's that quick when you're writing well-behaved sequence rules, especially arithmetic. We just want to test and make sure this works. Even if I went with a1, a1 would be -1.5 times n, which is 1, plus 11.5, which in turn gives us -1.5 plus 11.5. Draw this in here. Plus 11.5 equals 10. So we were supposed to get a first term value of 10. Now, when you look at this last example down here, this everybody's favorite, like a word problem. It says a person starts a new job with a bonus of $1,000 and then makes $3,000 for every month after that. So it says write a rule that describes the amount of money that the person has at any given month. So a couple things here. First one is, anytime it's a word problem, you probably ought to write out a few terms first. So, you know, our first paycheck, we start with $1,000 and then it goes up by 3,000 every time. So plus 3,000 on top of 1,000, that'd be, you know what, 4,000, and then we'd have another 3,000, it'd be 7,000, and then we'd have one with 4 zeros, 10,000, and this would just continue here. And so with respect to writing a rule for this, what are the two things we need? Well, again, we need the value of the first term, which we do have, and we need our common difference, which we do have here as well. So our rule for the amount of money at any given month would be given as We started at 1,000, so A1, and we're going up by 3,000 every month times n minus 1 here. And distributing, we get the nth term is 1,000 plus 3,000 n minus 3,000. And to put a negative 3,000 with the positive 1,000 would give us a negative 2,000. We get 3,000 n minus 2,000. This rule right here, if you want to interpret it, would give us, for a given month, would give us, I suppose, the money that this person has at a given month. Money at month. So in this case here, I suppose that we just wanted to write a rule that describes this. Kind of makes me sad that I didn't ask us to actually go use this rule. So let's try it. How much money then would I make in the third year? So that would be this year right here. So if I said the month was the third month, how much money would I make? I would make 3,000 times 3 minus 2,000, which if I continue my work here is 9,000 minus 2,000, would mean that I have a monthly dollar amount of $7,000 here. So you can see that these are actually, sequences are very good at describing word situations, especially if they're linear. Okay. Cheers.